que je suis très content d'avoir l'expérience ici et d'apprendre de Paul Tapenier, Raoul Madriaga, Albert Tarantola, beaucoup de grands chercheurs ici. Et j'ai très, how do I say, I was very lucky, I'm very fortunate pour cette expérience. Et aujourd'hui, je voudrais retourner quelque chose à vous dans cette expérience et je commence maintenant. Okay. Do I need this? You don't have a, it's a little difficult to do this and I'll try. Okay. We're going to spend 20 minutes on this demo. And here's the news. Everything I understand about earthquakes is contained in this demo. And it's not very complicated. And the fundamental riddle of earthquakes is that though the forces that drive earthquakes are absolutely steady, earthquakes are not. They occur very rarely, all of a sudden. And I submit to you that you need 4 things to create earthquakes. If any of these 4 things are missing, you don't get earthquakes at all. If you have these 4 things, you only get earthquakes. Okay, so what are they? They're the steady motion of the plate's interiors, which is going to be represented by steadily cranking my casting reel. It's connected by a very low stretch cord to a rubber band. That rubber band represents the elasticity of the Earth's crust. Okay, so the Earth's crust is elastic, it's rubbery, it's just very stiff rubber. And they're connected to a mass, my kitchen countertop samples here, which have a rough lower surface. We've sandblasted this surface. And it's sitting on top of industrial non-skid, friction. So the 4 elements: steady motion of the plate's interiors, elasticity of the Earth's crust, some mass in frictional contact with the surface. Okay, so my job is to just crank steadily. Your job is to just watch what happens. Okay, so we waited a couple hundred years, and then suddenly we'd have an earthquake, right? And then we would wait, and we would have an earthquake again. So let me ask you a question. Were all the earthquakes the same size if we measure size by how much they moved? Were they? I want to hear it. No. Were they all separated by the same amount of time? This is very bad news. If I can't make steady, repeating earthquakes with industrial strength sandpaper and steadily cranking this, we're never going to get them in the Earth. Because undoubtedly, all of these parameters are more variable in the Earth than they are in this experiment. The value of the elasticity changes if it's granite, if it's basalt, if it's sediments. Friction on the fault is probably not nearly as smooth as this. If I put my hand down this, it all feels identical to me, and it would to you too. The surface that's in contact isn't changing. The mass is fixed. And yet I still don't get regular repeating earthquakes. And so this means that despite 40 years of efforts to predict earthquakes, seismologists have had to swallow the bitter pill that they are not clearly predictable. And if you ask yourself, okay, what is the course? What is the cause of this variability? Well, if I did crank steadily, that can't be it. This rubber band never went outside of its linear range. That can't be it. The mass didn't change. There's only one thing that can be different, and that's friction. Even though it feels very, very uniform to me, tiny differences in the friction at one point and another control the whole story. Friction controls the whole story of when earthquakes rupture and when they don't. Okay, let's look at it again and let's ask the question, after a big earthquake, do I wait a longer time? This is a demo, by the way. There are no right answers. Whatever you see is what happens. Right? Maybe, but not very impressively. And if we did the alternative, we could say, well, I asked you whether or not we wait a longer time after a bigger earthquake. We could also say, if we waited a longer time, should we next get a bigger earthquake? You'd get the same answer. Probably not. And despite the fact that time and slip predictable earthquakes, which is what those theories are, have been around since the 1980s and are very rational, right? We would expect that if I can, for some reason, go a long time without it, I'm going to bigger earthquake afterwards. It doesn't work. And that's also what we've seen. So when seismologists get on the news and say, oh, well, we are overdue for an earthquake on the southern San Andreas, so it's going to be bigger, they're wrong. We can't say that. There's nothing in the evidence, mechanically, that says we have the ability to say that. And let me show you something else of interest. Okay, so watch the stretch in the rubber band. All right, we've just had an earthquake. Look at this. It's almost as taut as it was right before the earthquake. Let me show you again. So there's right before, right after. It's only changing by about 10 or 15% after an earthquake. This is exactly what we understand faults to do. Stress drops on faults are only about 10 or 15% of the total stress the fault is under. What does this mean? It means that in a seismically active area, you're walking on eggshells. Most faults spend most of their lives very close to failure. And this means something else. We tend to say after a big earthquake, well, now we're going to wait several hundred years until that earthquake occurs again. After a big earthquake, we tend to argue that the probability of a large earthquake has now plummeted and will need some long time to rebound. But this tells you that's probably a lie. Because even right after that big earthquake, we have a lot of stress in the system. We haven't really dumped it. It's a very rare earthquake that completely drops the stress. The Tohoku magnitude 9 earthquake was probably one of them. Loma Prieta in 1989, just a magnitude 7 is probably another. We can't find many. So when we say to people after a big earthquake, well, okay, now all is clear, we're lying. The system is still loaded in almost all respects. We never have an earthquake in this system that completely drops the stress. Put another way, the sliding friction is not that much lower than the static friction. And so the system never really dumps all the stress. Okay, what else can we say? If I load this all the way up till it's just about ready to go, what happens if I lift the top brick? I want to hear it. Yeah, because what? I've unclamped the fault. So there's a force balance here. The force resisting motion is the weight of these bricks times friction. That's about 0.5. And that's got to be balanced against the force pulling on it, which is the elasticity of this spring times its length change. So if I have the resistance, then it can go. So if we can unclamp a fault, even a little bit, and it's close to failure, we can trigger an earthquake. We don't cause the earthquake, we can trigger it if it's close to failure. And by the same token, if I get this just about ready to go, and I add a little bit more shear stress, again I can trigger an earthquake. But this only works if it's close to failure, because now nothing happens. Now nothing happens. So if a fault is close to failure, then what we call the Coulomb Criteria applies. In other words, if we increase the shear stress or unclamp the fault, we can trigger yet another rupture. And that's our easy way into an exceptionally hard problem. We may never know when that next big earthquake is occurring. But if we can understand where we have lifted a brick and pulled on the spring, we know where aftershocks and subsequent main shocks are more likely to occur. And similarly, we know if where we put on a brick or ease the spring, those aftershocks are less likely to occur. Now let's take this a little farther. I'm going to get the gouge off the fault. Okay. So you saw the behavior of a two-bricker. Okay, Now, what if I now crank at the same speed and have a one bricker? So what am I going to get? Am I going to get more frequent earthquakes or less? How many think it's more? How many think it's less? Okay. Are these earthquakes going to be more larger or smaller in terms of the amount they slipped than the two brickers? How many say larger? How many say smaller? Okay, so let's see how your intuition went. Yes, they're about twice as frequent, right? And about half the slip. Okay, that makes sense, right? So if you can find a place where we have only half the mass involved, for the same fault, with the same slip rate, with the same elasticity, we can have more frequent and smaller earthquakes. And of course, the San Andreas has such a spot. It's called Parkfield. We get magnitude 6, 6.5 earthquakes every 30 or so years, whereas in the northernmost and southernmost part of the San Andreas, we have places where we have magnitude 8s that occur every several hundred years. So if we can find such a place, the interesting thing is everything else is the same. Same friction, same elasticity, same speed. All right, let's take this one step further. What if you can see that this part of the surface is polished. This was supposed to be on the top of the kitchen counter. What if I turn this upside down? All right, so now I have dropped the friction on one side of the fault to 0. The other side is identical to what it was before. Now what am I going to get? Okay, so how many people think that this is now just going to creep without producing any earthquakes at all? Hands. How many people feel that we're going to have earthquakes smaller but even more of them? Okay, so we're kind of split there. And you're both kind of right. It's very interesting. Oh, I see. The rubber band got underneath it. Okay, here we go. So it's not completely creep, is it? We're actually getting smaller and more earthquakes accompanied by some kind of creep. Well, we have this place on the San Andreas too. It extends from Parkfield to the southern San Francisco Bay Area. It's about 100 kilometers long. And the interesting thing about it is that the friction is only 0 on one side of the fault. One side of the fault is granite. The other side is this green schist, which is very, very slippery clay material. And that's where we get more earthquakes than anywhere else on the San Andreas, but they're very, very small. Everything else is the same. Same elasticity, same fault speed. So what's remarkable is how this diversity of behavior can all be explained in a very simple system. Now you might say, well, okay, this is great, but this is all these earthquakes are in isolation. But the San Andreas and the North Anatolian Fault, they're 1,000 kilometers long. And as far as we know, they haven't had 1,000-kilometer long earthquakes. So most faults must get earthquakes in some kind of series. So what can we say about that? So let's connect them up in series. Okay, so now we have a very different system. And again, you have to make a prediction because why else do a demo? Okay, which guy's going first? How many people think it's this guy? How many people think it's this guy? How many people think it's this guy? Okay, who's going second? This guy? This guy? This guy? Who's going third? Okay. This could be a trick question. Let's see what happens. Gets really interesting really fast, right? So this guy went first, kind of second and third, because it took several times until this spring was sufficiently loaded for this guy to go into the action. This guy went. Once this guy went, then it unloaded this spring, and then they could all go together. Sometimes they all pretty much went together, but more often they went singly. And that's exactly what we see in faults. In 1992, we had an earthquake in Southern California called the Landers earthquake. And there were 3 faults that wanted to produce a big earthquake, and on a good day they could produce a 6.5. But within a matter of 20 seconds, they all got together and ruptured together, and we had a 7.5. But paleoseismic evidence suggests that's not typical for that fault. They tend to go separately. And this is a problem we have that further complicates earthquake forecasting and earthquake prediction, because we don't know whether or not this guy is going to take her sisters along with her. And it doesn't know either. And so sometimes, if the conditions happen to be right, we can have a much larger earthquake. And this happened on the North Anatolian Fault as well. But in general, we're going to have individual earthquakes. And this makes life very difficult for us. Now, the strength of this experiment is that you can see these things occurring in sequence. The weakness is it's a kind of a one-dimensional world we're looking at, right? They just can happen in a line. And that really doesn't begin to describe a lot of earthquake phenomena. For example, imagine that this is a megathrust surface. Well, there are interactions on that plane with small and large patches. And we know that those kind of things occur. Think about the San Francisco Bay Area. We don't just have the San Andreas. From west to east, we have the San Gregorio Fault, the San Andreas, the Hayward Fault, the Calaveras. Those probably interact as well. So the limitation of this experiment is it's linear. And that's why we created fishnet stocking stress. Okay. Now, to really see this, because it's very cool, I think it'd be far better, why don't you all come forward and we'll crowd around this together and we'll look at it. It'll be worth it. So what we're doing here is we've replaced, I also won't need this, we've replaced the rubber band with a elastic membrane. So this is a thin elastic membrane, the fishnet stocking, based on 100 years of industrial research, something, and it's extremely refined piece of a device. So this is the elastic membrane, and I'm going to just pull this frame along. And I have a slider down below, and it's just magnetically attached here. So this is the equivalent of that two-bricker that I showed you before, and let's see what it produces. So again, we wait a couple hundred years between earthquakes, but now what you can see is that it's affecting the stress all around. We see these wings that come out here with higher shear stress. We see tension here. We see compression. That this guy is influencing the field around it. You can keep seeing that pattern change. And like before, we don't release the stress completely. After the earthquake, we still have the wings, but before the earthquake, they're stronger. Okay, so the same thing we saw before. I don't think I need this anymore. All right, so now we're going to put in a little guy. And so, think of this is the two-bricker, this is the one-bricker. So this guy should be producing earthquakes at about twice the rate of this one, right? Well, let's see if that happens. Pretty good, right? This guy is happening more frequently. And there isn't a lot of interaction between them. But, if I take this guy and get him a little closer, life changes. All right? So now let's see what happens. Now things get interesting. This still has often one more earthquake than this. But when the big guy goes, the little guy goes too. This guy has become captive. He thinks it's a big guy. This is what the Hayward Fault is. The Hayward Fault fault is a couple hundred kilometers long. It's 20 or 15 kilometers away from the San Andreas. It has half the slip rate of the San Andreas. The San Andreas is 1,000 kilometers long, but they have similar recurrence. And that's because the Hayward has been captured by the San Andreas. It imagines it's a great fault, but it isn't. It's this situation. So now we can begin to see this kind of three-dimensional interaction. Now, even this is kind of too simple, because we know that on a megathrust surface, or with a bunch of parallel structural faults, we have a lot of different sections. So what I want to do now is just kind of randomly put some of these guys out here to kind of see what we're going to see. And I don't really have a particular plan on where they'll be. I want to make them random because I think that's kind of what we imagine that the little parts are. Okay. And now let's see what happens. And one of the things we're seeing is these guys are strongly interacting, right? This interacts a little with this. This guy is still captive, and this guy is kind of doing his own thing. But there is clearly interactions going on here and here. Now, let's do the same thing. Don't even look at it. Just close your eyes and listen. When you close your eyes, oh, that's random noise. But when you look, you see this is not random noise. These are very strong interactions that are happening. This is the signal that we have not tapped. This is the opportunity for us to be able to read the communication between these patches. They are strongly interacting. They are transferring stress between each other. It's not simple because you can imagine that this is still only a small fraction of the kind of interaction that are occurring, but they're there. And we mistakenly and forgivably assume that these are Poissonian processes, these are random occurrences. They probably are not. And the real opportunity ahead for all of us is to try to figure out how they interact, how they are talking to each other. It's not easy because we don't have a good visualization of those patches, but almost certainly that's what's happening in the system. Okay, now what I'd like to do is take this, now finally two-dimensional experiment, and show you in some slides some actual cases of earthquakes so we can kind of see this in 3 dimensions. But before I do so, I want to do one more thing. I want to do this. Okay? Now, I didn't crank, right? But we saw some earthquakes. Let's get it kind of on its own again. Now you need a weaker. I say something. Okay, what's that? That is not the simple elastic process I've been describing. That is sending a standing wave down here, right? So when I get this, there's a wave that's moving at the speed of sound of this table, a seismic wave, through here and causing some normal stresses. And some of these guys, that's just enough because they're close to failure and they release. Okay? That's what we call dynamic stress interaction. That's another whole game. We don't understand it well at all. I'm going to show you conflicting evidence for it being really important and really a bust. But this is clearly the frontier, understanding this interaction of these elastic, permanent stress changes and dynamic processes, because every large earthquake sends these waves. And if it's over magnitude 6 all around the world, then we have to understand that interaction too. Okay, so that's the setup for the slides. And now let me show you what I think of that. You can see why I had to have you up here, right? Okay, so I mentioned this 1992 Landers earthquake, the magnitude 7.3, that it occurred on 3 faults that got together. And these are the aftershocks that were recorded within 3 hours of the main shock. And you can see that there's some aftershocks way over here at Big Bear, one up here, one here. Most of them are along the fault. Now, the calculation was made long after the earthquake. But here's what happened 3 hours and 8 minutes later. We had a magnitude 6.5 earthquake in that zone. Now, why do we have these zones? Basically, if the fault were very short, the Coulomb stress zones at the end and at the sides would be about the same intensity. As the fault gets longer, the end lobes get larger and the middle lobes get smaller. If the fault were straight, the side lobes would be the same intensity, but the fault is curved, so the inside curved, it's curved like this, so this one is larger. These are the Coulomb stress changes. So in other words, if it's red here, it's because, going back to the first experiment, now you could say, even then you say, well, look, I could have gotten lucky. I could throw a dart on this and I have about a 50% chance of hitting a red zone, right? But we have 10,000 aftershocks. And the vast majority of these aftershocks are also in the red zones. Now you could still complain. You could say, yeah, but you have some earthquakes in the blue zones. That can't be right. Because no matter how close it is to failure, if you ease the spring or you add another break, you shouldn't get earthquakes, right? So doesn't that falsify the hypothesis? Well, maybe, but more likely, what should happen in the stress shadows, the blue zones, is the rate of earthquakes drops. And in the red zone, the rate of earthquakes increases. And that is borne out now by 30,000 studies. And we have software called Coulomb where anybody can make these calculations that I'm showing here. And what these many studies have shown is that part of earthquake action can be explained in this way. Not all of it, but perhaps 2/3 of it. However, here's this guy, David Jackson, who's been the kind of Groundhog Day of my career. Every time I show up at a meeting somewhere around the world to argue that this explains a lot, he's there to say that I'm all wet. And it drove me crazy, and then suddenly, this is what happens as you get older. I realized about 5 years ago, in all of the arguments that David Jackson and I have had over our careers, in retrospect, he's been mostly right. So I better start listening to the guy. And one of his arguments is retrospective analyses don't count, analyzing the Landers earthquake, because we already know what it produced. So there's too much bias. And whenever you study a case, there's a natural bias to try to explain what you're observing. In his view, the only thing that counts is prospective tests. Only if you're predicting the future does it pass his scientific test. So now I have to listen to the guy that I've decided that he's been right so often. So let me show you a couple of cases which are prospective. So here's one. This is a magnitude 6.2 earthquake that occurred in Kumamoto, Japan in 2016. And here's a calculation made by my collaborator, Shinji Toda, and he pointed out that 2 faults, the Futagawa fault and the Hinagu fault, are both in a stress Coulomb lobe as a result of this magnitude 6. So he presented this calculation to the press, which was published on April 15th, and the next day we had a magnitude 7 that ruptured both of those faults. So it's a blind test. And in fact, the aftershock distribution of that magnitude 7 is is rather consistent with the Coulomb calculation. Let's go back to Landers and say that while the Coulomb stresses are permanent, the response of seismicity is not. So we need to merge the Coulomb hypothesis with something called rate and state friction to explain how seismicity responds in time. And that's what the picture looks like when we do so. And you can see that this is a forecast of where we should see more seismicity, those are the red zones, and where we should see less seismicity than before, the white zones. So we made a forecast in 2005 for the next 10 years in that area. So here's our forecast, published in 2005. And we said, for example, that in this area there's a 92% chance that we will see a magnitude 5. And in that box in the lower left-hand corner, about an 80% chance of a magnitude 5. So how'd we do? We did get a 5, and we almost got 5s in that corner, but not quite. So you could say, all right, overall we did okay. How does it compare with the smaller earthquakes? Here are small earthquakes, and here's our forecast. So some things we got right and some things we didn't. We did expect and get a lot more earthquakes in the lower left-hand corner, but there were more earthquakes over here than we forecast. Okay, here's another case. Here's the site of a magnitude 6.5 in 2017. This is a national park that was destroyed by this earthquake. And here is a 10-year forecast we published in 2008 after the Wenshan earthquake, which is the green rectangle. So here is the background seismicity, the preceding decade of seismicity, just smoothed in the warm colors. And then here's how we thought that seismicity should change as a result of the stress contributed by the Wenshan earthquake. So you can see those two color patterns are different. Some are intensified and some are diminished. And here's what happened during that decade. So these two large earthquakes have occurred in regions where we calculated the likelihood of large earthquakes or magnitude 6 and larger earthquakes had increased. So these are the kind of efforts that suggest that Coulomb stress triggering here does indeed explain a lot of what we see. It's not predictive, it's a kind of a forecast, but hopefully useful. And that was kind of my worldview until 2012, when an earthquake occurred that changed what I understood to be the truth. So this event, this magnitude 8.6 off the Indian Ocean, is the largest strike-slip earthquake ever recorded, maybe by a factor of 10. So this is truly an enormous earthquake, and a very strange one. It looks more like a car accident than any kind of 8.6 you and I are used to. And I was at a Turkish restaurant with my wife, and my phone kept buzzing because earthquakes were occurring, and they were occurring all over the place, all over the world. Now, these are the earthquakes that occurred over magnitude 5.5 in the next 6 days. Now you look at this and you go, well, could this be something unusual? These are exactly where earthquakes normally occur. There's nothing in that distribution that's particularly different than what we normally see. And it just looks like, well, they're largely around the Pacific Rim with a few in Indian Ocean and Crete. But because I have a lot of rubber bands in my office and I'm a very sophisticated scientist, I have a lot of inflatable globes. And I put sticky dots on one of my globes where these magnitude 5.5 earthquakes were. And I found that I could put a rubber band around all of those earthquakes. So this is something that wasn't evident from a normal Mercator projection. And you can see that it looks pretty good if I center these rubber bands on the main shock. So I went running into Fred Politz's office and showed him that. And he said, oh yeah, that's the love wave radiation pattern. So Fred did a spherical harmonic calculation and got this. Now I ask you, which is better, Fred's show-offy calculation or my middle school science fair version of things with sticky dots? I think it's obvious, right? And what was interesting about this is what Fred is calculating here is not the magnitude of the dynamic stress, the stress imparted by the waves. It's the duration over some threshold magnitude. Because after all, if you just did this for the magnitude, all the stress is highest very close to the main shock, and as you move away, it gets very small. So that can't explain a uniform distribution of global aftershocks. And so this suggests that duration is very, very important. Now, why would this magnitude 8.6 possibly show global aftershock triggering since we've had much larger earthquakes, magnitude 9.2s, which don't? And the answer appears to be due to the love wave radiation of a strike-slip earthquake. So on the left are the love waves recorded at several places around the world of the 8.6 compared to the largest earthquake we've had in the last 15 years. And they're much smaller. And so what's unique about the 8.6 is it's a strike-slip earthquake, and the love waves do this. So if you look at the distribution in time of these earthquakes, you see something really remarkable. And you get this sudden increase in the rate of global magnitude 5.5 earthquakes. And we've cut out anything within 1,500 kilometers of the main shock. And what's interesting about this is I did the same calculation myself in the first day or two after the earthquake and convinced myself, well, they're higher than before, but not significantly so. Because I didn't believe that something like this could happen. And Fred came running into my office and said, did you see these global aftershocks? I said, no, Fred, I've looked and they're not. And he took me into his office and he showed me this plot, which was basically the same as my plot. And this is what it taught me. Everything that we consider our wisdom and our judgment can be bias. And I got by because I have a very good colleague who hit me over the head that I wasn't allowing myself to see something that was truly important. And when we saw this, we said, well, look, if this 8.6 can do it, what about all these larger earthquakes? So we stacked all those larger earthquakes, and you can barely see the signal. This one on the right is a Rorschach test. It's in the eye of the beholder. If you believe it, you see a signal. If you don't, you don't. So they don't show anything like the 8.6, even though by energy, they're up to 20 times larger. But then something else. Since the love waves do this, you would think that what you're doing is stimulating strike-slip faults. And therefore, we should look to see the ratio of strike-slip global earthquakes to others. And that shows something really remarkable, that normally the global earthquakes, 25% of them are strike-slip. And right after this thing occurred, 70% were. And then that fades with some kind of rapid Amori decay. And that suggests that out of the maybe 40 or 50,000 possible sites of magnitude 5 earthquakes around the world, a few were close enough to failure that when I hit the table, they ruptured. Now there's one more interesting part of this story, which is it turns out that this earthquake occurred after a couple of weeks with very few global large earthquakes. So here's the rate of global large magnitude 5.5 earthquakes. And you can see that compared to the previous decade, this had the lowest rate of any. And that none of the other large earthquakes occurred before a period of low rate. So here's the idea. Imagine that you have an apple tree. And that apple ripens, that tree ripens apples. And those apples fall at some rate, a couple a day. Let's say for whatever reason, none have fallen for a couple of weeks. Now, what do the seismic waves do? They basically rush up and shake the trunk of the tree. So if you have more over-ripened apples, maybe they'll fall at a higher rate than normal. So maybe it's a combination of these two factors that's important. So what I got out of this study was that maybe dynamic triggering is important, but extremely rare. It takes a very, very large earthquake and possibly a very large strike-slip earthquake to do it. But maybe that's wrong too. You know that we've just had 3 magnitude, we've had an 8.2 and two 7.2 earthquakes in the last year in Mexico. In this picture, there are 3,300 magnitude 3 and larger earthquakes in a month. During the same month, California had 30. Now, what's interesting is that the Puebla earthquake up here occurred 12 days after the 8.2. Is there a dynamic relationship there? We calculate that the chance that they're coincidental is about 1 in 3,500. That's a pretty big number, but do you remember that the Puebla earthquake occurred 2 hours after the annual earthquake fire drill in Mexico City? Earthquake drill in Mexico City? You know what the probability of that is? 1 in a million. So the chance that it's 1 in 3,500 and it's just coincidences is very possible. But what if that's wrong? In what way could these earthquakes, could they be communicating? They're too far apart for the static stresses to matter. So maybe dynamic triggering is important. So here's a calculation we did of the shear stress on the Puebla rupture produced by the Chiapas main shock, and the effect is almost a bullseye and about 3 bars. That's about 10 times what typically turns on shocks in static Coulomb triggering. But when we looked at the unclamping stress, lifting the brick, it's twice as high, and now it's nearly a bullseye. So that raises the possibility that if there were fluids under very high pressure and you suddenly reduced over about 20 seconds the clamping forces, could fluids permeate the fault, diffuse around the fault, and make it more slippery to trigger a rupture? I don't know the answer. I don't know that anybody knows the answer, but we want to keep looking for things that we might otherwise miss. And if there is a signal here, it's probably not a Coulomb phenomena. It's probably related to this unclamping, in which case that 12-day period would be related to the diffusion of fluids rather than anything else. Okay, so that's dynamic triggering on a large scale. What about on a small scale? What about for really, really tiny earthquakes? Is that possible? Well, a paper was published by Emily Brodsky and Karen Felser in 2006 arguing that even magnitude 2 main shocks can trigger magnitude 2 aftershocks up to 50 kilometers away. And the only way that could be explained would be by dynamic shaking. Now, could there be a problem by how they define an aftershock? They said an aftershock is anything that happens within 5 minutes of the main shock. Now, very few magnitude 2 to 3 earthquakes have aftershocks. So you have to stack huge numbers of these to see any aftershocks at all. So here's the question. If you have a magnitude 7, and a month later you have a shock up here, and 5 minutes after that you have a shock down here, is this guy an aftershock of that main shock, or are they both aftershocks of the magnitude 7? You really can't tell. So we published a paper where we said, no, they're not dynamically triggered. So I want to show you 3 falsification tests of their hypothesis. Now, their argument was this, that when they stacked all these aftershocks, the decay looked nothing like a static decay. It extended out too far and was too large. And these are all the shocks that occurred within 5 minutes of the main shocks. Okay, if these are aftershocks, then this distribution should look nothing like the 5 minutes before the main shocks, right? So, here's what the 5 minutes look like before the main shocks. Almost identical. And if you take those 2 spline fits and you put them on top of each other, the only place where aftershocks have a higher rate than main shocks is within 300 meters of the main shock, which is the static limit of the interactions for those events. Okay, here's another test. The aftershock cannot occur until the waves reach it, right? You can't have premature aftershocks. That would violate causality. But look at very, very short periods of time. We need to see that this decay stops at the moment before the seismic waves reach it. So now we need to look at a very short space of time. Rather than 5 minutes, we'll look at 1 second. And you can see that the decay continues right across this line. So this is improbable before the S wave and impossible for the P wave, but it's still there. So this shows they're not aftershocks. Okay, one more. The only observable feature of aftershocks that distinguish them from main shocks is the fact that they have a Mori decay. Their frequency decays with time. That's the only thing that we really can establish as unique about aftershocks. If we look at the earthquakes within a kilometer, all within the static range, they show an Mori decay. If you look at earthquakes more than 10 kilometers away, well outside the static range, flat as a pancake, no Mori decay. So they're wrong. It can't be right. These little earthquakes, at least this experiment, is not demonstrating dynamic triggering. Okay, why am I showing you some study which I'm just saying is wrong? What's the point of that? There's a deeper point I want to make. All we can do in science is falsify hypotheses. We never prove anything right. We are responsible for proving things wrong. On the other side, Felser and Brodsky are doing the right thing. They are promoting ambitious hypotheses, which, if correct, would be profoundly important. So for science to work, we both need to propose exciting new ways of thinking about things, and we need, as best we can, to annihilate those ideas if they don't fly. That's the deal. That's the compact that we have to do as scientists. We're not behaving as scientists if we just follow in previous footsteps, and we're not behaving as scientists if we don't try to falsify what has been proposed. So really, the highest compliment I can pay those two scientists was to fully test their hypothesis. Where does this lead us? We've done other studies of dynamic triggering. This is the 2004 earthquake. And basically, in this big case, the dynamic triggering is a very complicated beast because those waves are bouncing off lower layers and coming back up, and the rupture is speeding up and slowing down, and all of that starts to matter, so it's a difficult business. But at this point, the conclusion that I reach, and the way I would like to end this talk, is to say most earthquakes converse by static stress. Some earthquakes, through dynamic stress, are able to nudge faults into failure. Maybe that's only really big earthquakes. Maybe it's also occurring at a smaller scale. That's where the frontier is in trying to understand the complicated role of dynamic triggering. And with that, I'd like to thank you and my collaborators.
Okay, thank you very much for this exciting presentation. Questions, comments? Who will be the first one? Okay.
Thank you, Ralph, for this talk. So in your demo here, you've been showing the case of the captured smaller fault, and you're mentioning the Hayward fault, which is a big thing right now because there is this haywire things where USGS is suggesting that it could go by itself.
Yes.
So how does it go together?
So my view, I think the historical evidence is not that every time the San Andreas ruptures that the Hayward fault ruptures. Their connection isn't that strong because they're still 20 kilometers apart. Rather, its recurrence behavior with events every several hundred years is rather similar to the recurrence behavior of the San Andreas. So they interact with each other in that sense. So the interaction is weaker than if they were much closer together, but still, if it weren't for the San Andreas, the Hayward fault would behave very differently. That's what I would propose.
So you showed us many things with the Coulomb failure criteria, etc. But is there any story about elasticity? Does elasticity change? Does it cause some difficulties Is it really elastic all the time?
That's a great question. So clearly elasticity changes in space because of different materials and different material properties and different layers. Does it change in time? Well, there's viscoelastic response of the lower crust, and that causes faults to reload, and that's been ignored in this experiment. So there is clearly an oversimplification here of the way in which faults can be reloaded rapidly from the viscous flow, and for the most part that's occurring below the brittle crust, but maybe some of that is also occurring internally. And further, if fluids are important in the crust, then there's some secondary phenomena that's not elastic but changes the behavior of faults on different time scales. So my rubber band is certainly an oversimplification of elasticity. Nevertheless, I want to emphasize that experiments like this show us that friction is probably still the most important variable and the hardest for us to understand. Faults must, if you think about it, with time, with cumulative slip, faults would get slipper and slippery, and all old faults would creep, right? And new faults would have large earthquakes. But that's not what we see. So there are other phenomena that make faults rougher in time, in addition to the features that build up gouge and make them smoother. And that is variable in space. In the 1966 Parkfield earthquake, there was a magnitude 5, 18 minutes before the main shock, a kilometer to the north. And in the 1934 earthquake, there was also a magnitude 5, about a kilometer to the north, some minutes beforehand too. And that suggests that there's some rather fixed asperity that plays some role in releasing that earthquake. In the 2004 Parkfield earthquake, it didn't happen at all. So this suggests that some asperities are fixed, some get reshuffled by every event.
Yes, what is your feeling about the effect that tides may have on triggering earthquakes?
Another great question. So there is enough research to show that in mid-ocean ridge events, some mid-ocean ridge events, and some crustal events on land, there is a tidal signal. And that tidal signal seems to be most important when the solid earth tides align with the regional stress. So if the tidal earth orientation happens to align with the tectonic stress, then the fault becomes most sensitive because those are the stresses that tend to trigger it. And when that happens, you see an effect. It's generally a very small effect. Earthquake, tremor, and slip, many of those cases show tidal triggering as well. So the first thing that tidal triggering tells us is that there really is no lower threshold at which this phenomena works, because those stresses are extremely small. They're about 1/10 to 100th of what normally triggers aftershocks, but still tidal triggering is relatively rare. And there is disputed evidence for its role in the triggering of very large earthquakes.
Okay, more questions? So maybe I have one, a provocative. So what are the latest predictions for the Bay Area earthquakes?
Well, it's interesting that in the USGS hazard model, the hazard is about twice as high on the Hayward Fault than it is the San Andreas. You have to ask yourself, is this possible? Could the hazard be twice as high in a fault that has half the slip rate as the San Andreas? I think this is an open question. There have been not only magnitude 8s on this northern San Andreas, there have also been magnitude 7s. I think maybe we are too attached to the idea of a recurrence interval and a buildup of stress as we get there, which is not how this thing behaves. So yes, we should be concerned about the Hayward Fault because of the high density population. But in our business, we have been humbled over and over again. Every time we say, like we said in 1985,
the Parkfield earthquake would occur within 5 years. That was the forecast. Well, that Parkfield earthquake arrived kind of like my wife, egregiously late, but well worth waiting for. So we have to be really careful in the forecasts we make. We generally are wrong. I would like to close just by saying that Kelsey Linton is the person who, while she was a high school student, built a Quakecaster with me. When I realized I had what I had on my hands with her, I bought out all her babysitting hours. And Jeremy Shar from Brown University built a fishnet stocking stress and figured out the fantastic way in which we can magnetically attach the sliders without them interacting sideways in a magnetic way. So it's great to be able to acknowledge their contribution to this work. Thank you.